So, now we discuss the smoke management techniques, how we calculate the total air leakage. So, it's given by the formula Q is equal to 2610A delta P raised to power 1 by 2, where Q is the airflow leakage in CFM, A is the total leakage area in square feet, and delta P is the pressure differential to be maintained in inches of water. And in SI units, this formula is given by Q is equal to 840 A delta P raised to power 1 by 2, where Q is the airflow leakage. Only the units are different. It is liter per second. And the total leakage area is in square meter. And delta P is the differential pressure in pascals. So how we calculate the total airflow? The total airflow requirements is equal to the sum of the leakage through the gaps in building construction, because building always has some gaps or the cracks or the penetrations for which some leakage area is considered as the flow rate through that is Q1, and the leakage around the doors and windows, that is Q2. And we have to assume 3 open doors at a time. That means one is the affected door where the fire is there, and one is the main door at the entrance from where the people are escaping will be normally open, and any other floor in the intermediate story that is considered to be open. So 3 doors are normally assumed to be open for the calculations. Now, how we calculate the leakage CFM from the building construction elements. So NFPA 92, it gives this leakage data from the construction elements. So there is a term called area ratio, which is basically area ratio from any component, whether it's a wall, ceiling, or floor. It is the area of the leakage through that wall divided by the total wall area. So basically it will be there for the different elements of the construction, for the exterior building walls, for the stairwell walls, for the elevator walls, for the floors, and likewise for the ceilings. So for the stairwell walls, for the average tightness construction, the area ratio is mentioned to be 0.11 into 10 raised per minus 3. And likewise for floors, for an average tightness, the area ratio is 0.52 into 10 raised to power minus 4. How we calculate the leakage areas around the doors and windows? Now there are basically two types of doors that will be there in a building normally. One is a single leaf door of size normally 3 feet by 7 feet, and it has a crack length which will run along the periphery of the door, that is 2 widths and 2 heights. So 3 plus 3, 6 plus 7, 13 plus 7, 20 feet is the crack length, and the gap which is assumed to be 0.006 feet, that is around 2 mm. And thus the leakage area across the single leaf door along the periphery will be 20 feet into 0.006, that is 0.12 square feet. So similarly, if it's a double leaf door, which is there in the picture, for considering a size of 6 feet by 7 feet, the total crack length is now here 2 widths plus 2 heights on the periphery, and 1 is the central height. So the total perimeter crack length becomes 33 feet. And for a gap considered of 0.006 feet, it becomes 0.2 square feet as the leakage area. Leakage to the open doors, it is calculated from the formula Q is equal to V maximum into A door, where Q is the flow rate through the one open door. V maximum is the maximum velocity across the open door. It is stipulated to be 200 FPM or 1 meter per second as per IBC, and A is the total effective door area through which the leakage would be happening. So, and if the premises it includes several doors in parallel, then the effective leakage area has to be a numerical sum of all A1 plus A2 plus A3 plus A4. And while if the doors are appearing in series, then the effective area will be 1 by A1 plus 1 by A2 plus 1 by A3 plus 1 by A4, overall raised to power 1 by 2. That gives the effective leakage area. So for the total system selection, we we need to know the fan capacity, how it can be calculated, that we have seen already, the leakage areas and the leakages through the building construction, plus the leakages through the doors and windows, and the leakage which will happen to the open door when the doors are open. So we can calculate the total volume flow rate, select the fan. We may take a safety factor for the unknown elements, and then that gives the fan capacity. Then we, based on the building construction and the total location of the fan, we need to find out the total resistance of the distribution system, the pressure drop in the vertical run, in the grill, and in the duct. So we can calculate the fan static pressure based on the total pressure and the velocity head at the fan discharge. Then the supply outlets or grills at each platform, they are designed at a velocity of 500 to 600 fpm. Then, as we mentioned earlier, that there is a venting requirement to prevent overpressurization, and also, otherwise it can cause a problem in opening of the doors. So how we calculate the relief air? That is by calculating the air leakage when all the doors are open, minus when the condition when all the doors are closed. So that is the relief air, is a differential of the two, and then we can size the vent relief and damper by considering it at a velocity of 2000 fpm. At the same time, we need to maintain a minimum pressurization level of 25 pascal in the staircase. So now we will come to individual calculation, one case study each for staircase pressurization, lift lobby pressurization, and lift well pressurization. This is here we are considering a building extending from ground floor to 25 floors. That is, in all, there are 26 floors, and the door size is assumed to be 1200 wide by 2100 high. A single lift door and a gap of 5 has been considered. So the picture is showing two lifts with the lift lobby and the adjacent staircase, stairwell, and with the single lift door in each case. So how we calculate the staircase pressurization? As we saw earlier, we need to maintain a pressure differential of 50 pascal. Egress velocity through open door should be around 1 meter per second. So if we are considering 26 floors, and that means, and we have to consider 3 doors open. That means at a time there will be 23 closed doors. So how we calculate the leakage across the closed doors? We have to find out the air leakage air gap, which is the perimeter, that is 2 into W plus H. So we are considering door size of 1200 by 2100. So putting these values in this formula, we get the total leakage length of 6600 mm, and then considering air leakage gap of 5 mm, the total leakage area works out to 0.033 square meter. So from the formula 2610 into A into root P, which we studied earlier for calculating the leakage past the closed door. So we can putting these values in this formula 2610 into 0.033 into under root 50, we get the leakage past one closed door is 609 CFM. So considering now, since we have 23 closed doors, 609 into 23 is 14,007 CFM, which is the total leakage across all the closed doors. Now leakage to the open door considered of size 1200 by 2100, that is a leakage area of 2.52 square meter. The formula for calculating the leakage is A into E into 2118.9, where Q is the air quantity in CFM, A is the leakage area in square meter, E is the egress velocity 1 meter per second, and 2118.9 is the conversion constant. So leakage air through one open door, putting the values in this formula, 2.52 into 1 into 2118.9 gives total leakage to one open door as 5340 CFM. For 3 open doors, it will be 5340 into 3, that is 16,020 CFM. And total leakage in CFM is thus 14,007 plus 16,020, that is 30,027 CFM. So we can select this fan of capacity 30,000 CFM. Now coming to the case of lift lobby pressurization calculation, here we need to maintain pressure differential of 30 Pascal. Otherwise, the calculation is similar to the staircase pressurization calculation. Egress velocity, which is to be considered, is 1 meter per second. Total number of floors are 26. And the single lift door size assumed to be 1200 by 2100. Leakage length is the perimeter 2 into W plus H, which is 6600 mm. Considering air leakage gap of 5 mm, the leakage area becomes 0.033 square meter. So as we saw earlier, the formula for calculating the leakage air quantity is Q is equal to 2610 into A into under root P. So leakage to one closed door, that is 0.2610 into 0.033 into under root of 30 is 472. So here we have 23 closed doors. So 472 into 23 is 10,856 is the total leakage across all the closed doors. And then considering now again the 3 open doors, the air quantity rushing out of the open door will be A into E into 2118.9. That is for the door size of 1200 by 2100. That is a total effective area of 2.52 square meter. Here we can calculate the leakage quantity through the open door as 2.52 into 1 into 2118.9, that is 5340 CFM, and for leakage through 3 open doors it is 5340 into 3, that is 16,020 CFM. So the total leakage to the closed and the open doors becomes 10856 plus 16020, that is 26876 CFM, or 27,000 CFM is the fan capacity for the lift lobby. So this is an example for lift well pressurization calculation. Again, lift wells are to be pressurized at a differential of 50 Pascal. Egress velocity is 1. Total number of floors are 26. So here the door size assumed is 1000 by 2100, only with the difference that it is a double lift door. So for the leakage gap, it will have the perimeter plus 1 central height, that is total will be 8300 mm perimeter. Considering air leakage gap of 5, the total leakage area becomes 0.0415. So leakage area through one closed door, putting the values in this formula, we get 765. For the leakage across 25 closed doors, it is 765 into 25, that is 19,125. So then there is only one open door in case of lift well. So the leakage past that will be Q is equal to A into E into 2118.9. So it can be calculated as 2.1 into 1 into 2118.9, that is 4447 CFM. So the total fan capacity becomes 19125 plus 4447, that is 23572, or say we can select a fan of 23,600 CFM. So that was about the lift well pressurization. Now we can come to another assignment which gives the total leakages across the building structure and in totality. So here is an example to calculate the pressure requirement for an office stairwells where we have 5 floors. Each floor is 17 feet high and 28 feet wide and 48 feet long. It has 2 single leaf egress doors of size 3 feet by 7 feet each, and 1 double leaf egress door of size 6 feet by 7 feet. And we have to assume 3 doors open, and we have to maintain a pressure differential of 0.37 inches between the stairwell and the adjacent space. So how we go about it? This is the table which we saw earlier for the area ratio. That is the area leakage area calculation for the building structure. So this is here we have tabulated all the leakage elements in the structure. We have the walls, we have the floor, we have the ceiling, we have the doors, 2 types of doors. So we can calculate the total leakage area in the floor. So if we consider the leakage area for the walls, the length and width of the wall is 48 by 28, 48 by 28, and height was 17 feet, and height is 17 feet. So that gives the total perimeter of 152 feet, and the area is perimeter into height, that is 2584. And we saw that in this table that for the walls, for the average construction, the area ratio is 0.11 into 10 raised to power minus 3. So considering that area ratio into 2.2584 square feet, the total leakage area to the walls is 0.28 square feet. Likewise, the floor area is 48 by 28, 1344, and for average leakage, average tightness, the area ratio of leakage is 0.52 into 10 raised to the power minus 4. So multiplying this ratio by the floor area, we get the total leakage area from the floor, that is 0.07 square feet. Same is the case with the ceiling. So again, the leakage area in case of ceiling is 0.07 square feet. Then we have two doors. One is a two doors, 7 feet by 6 feet. Gap length is 20 feet, which are the single leaf doors, and the door crack size is 0.006 feet. So the leakage area for two doors becomes 0.24 square feet, whereas for the double leaf door, we have a central height also, which gets added. So it is a 33 feet gap length, and the total leakage area is 0.2 square feet. So total leakage area per floor becomes the summation of all these areas, that is 0.86 square feet. So how we find out the total leakage? Now there are three elements. One is the Q1 is the airflow through the gaps in the building construction, airflow around the door gaps, Q2, and Q1 plus 2 is K into A into delta P raised to power 1 by 2. So here, how we can calculate it? This formula constant K is 2610. So 2610 into 0.86, which is the total leakage area in the floor. So into 0.37, which is the pressure differential in inches, which is to be maintained. So we can calculate the total volume flow rate across all the building structure elements on one floor, works out to 1365 CFM per floor, and we have number of floors for the stairwell as 5. So the total floor rate for the 5 floors become 1365 into 5, which is 6825. Then we have to consider 3 open doors, which are two of them are single leaf, 3 feet by 7 feet, and one is the 5 feet by 7 feet. The total area becomes A1 plus A2 plus A3, since these are the doors in parallel. So we have the effective area is 77 square feet. And to find out the air leakage across the open doors, we have the formula Q3 is V maximum into AE, as we saw earlier, where V maximum is the maximum egress velocity, that is 200 FPM, and AE is the effective area, that is 77 square feet. So the total air quantity of leakage across the open doors is 15,400 CFM. So total airflow pressurization is Q. Total is the leakage to the gaps in the building construction, leakage to the door and window gaps, leakage to the open doors. So that becomes 6825 plus, this is 6825 plus leakage to the open doors 15,400, that is 22,225, say 22,500 CFM. So, and how we calculate the supply outlets? Suppose we have the 5 floors, that means we are supplying around 4,800 CFM at each supply outlet, and we need to maintain a velocity of around 500 to 600 for selection of the supply outlet grill. So we can give an outlet size of 4,800 divided by 600, that is 8 square feet, or an aspect ratio of 4 feet by 2 feet grill can be given. Now, venting requirements to prevent the excessive pressurization, that we told that it is to be designed based on the differential of the airflow leakage when all the doors are open minus when all the doors are closed. So the total air requirement with 3 doors open was 15,400 CFM, and the total air leakage from the envelope is 6825, and that is 15,400 minus 6825 is 8575 CFM. So we have to design the relief damper that should be able to maintain at least minimum 25 Pascal in the stair shaft, and this can be then sized for 8575 divided by 2000 FPM velocity, that is 4.28 square feet area cross section pressure relief damper can be sized. So that was all. I think the calculations are clear to everyone. Thank you so much. Thank you.